Hi, this is a quick tutorial on how to solve a linear programming problem using the Swag Media website. So this is a dedicated software which will help us work really quickly through such a problem. I'm taking this example of a cycle manufacturing company which produces boys and girls bicycles. The company has the capacity to build up to 400 bicycles per day and have orders to make at least 80 girls and 100 boys bicycles per day. The first thing I need to do when I try to solve such a problem is define the variables. So as you can see, this is a Word document, and up to here we've got the actual task, and here I've started working the problem. And to define the variables, I chose boys bicycles to be X and girls bicycles to be Y. And now I know that they can make up to 400 bicycles a day, so X plus Y, boys bicycles and girls bicycles, they can make up to 400 a day. They've got orders of at least 100 boys bicycles and at least 80 girls bicycles, so X greater or equal to 100, Y greater or equal to 80. And there is also a piece of information here about their capacity. It takes 3 hours to completely build a girl's bicycle or 4 hours for a boy's bicycle, and the company has enough employees to supply 1,400 hours of labor. So let's add that to our constraints. So 4 hours times the number of boys bicycles plus 3 hours times the number of girls bicycles needs to be up to 1,400 hours. Yes. And then we want to maximize the profit, and as a result of the price they sell the bicycles, the profit from each of the bicycles is $120 for the girls and $110 for the boys bicycle. So the objective function in our case here is $110 per boys bicycle plus $120 per girls bicycle. That gives us the total profit, and that is the objective function. So I take those equations and enter them into the website, which is here. So I've got the objective function and the constraints, and once I press solve, I come up with the graph here, and I've got the feasible region, and all I need to do now is take a snip of this screen and add it to my document. So to find the maximum profit, we need to plug into the objective function the coordinates of the vertices of the feasible region. And so I have added this, and as you can see, I've got the feasible region, where anywhere inside the feasible region, like for example, if we chose to build 156 boys bicycles and 150 girls bicycles, that would be inside the feasible region. So this satisfies all the constraints. But to maximize the profits, I need to investigate the vertices. As you can see, the vertex where the maximum profit is obtained is 100, 300, so 100 boys bicycles, 300 girls bicycles, and that profit is of $47,000. Now, the next thing I need to do, because all this has been worked by the software, is to make a statement. The maximum profit is achieved when the manufacturer makes 100 boys bicycles and 300 girls bicycles. This profit is $47,000. All right. For task 2, The cycle manufacturing company has employed a research company to gain consumer information and found that children ride bicycles in the ratio of boys to girls of 3:2. The cycle manufacturing company still wants to maximize their profits, but also be more in line with the ratio. Investigate using the existing constraints how they could maximize their profits if they produce bicycles at a ratio of boys to girls bicycles between 2:1 and 6:5. Now, what this means is that for two boys' bicycles, we produce one girl's bicycle. To make them equal, I have x is equal to twice y. And the same here, so 5x is going to be equal to 6y, but these are supposed to be inequalities. All right, so let's move on to how we write these inequalities, because they need to be between the new constraints. So we keep the existing constraints and we add the new constraints of x less or equal to 2y and 5x greater or equal to 6y, and we enter those constraints in here, and when we solve we get a new feasible area with new vertices, and we notice that the maximum profit is of 45,230 and 0.7692, and this happens when we produce 215.3846 boys bicycles and 179.4872 girls bicycles, but that cannot actually be. So I've taken a snip of that and added it to our document. So the max profit is obtained at this vertex, but we cannot have fractions of bicycles. We cannot have 215.3846 or 179.487 bicycles. I'll therefore zoom into this vertex and find the closest points with whole numbers as coordinates. All right, so we'll go back to here and I'll do the x, as this is 215, I'll do x at 200, between 210 and 220, and the y is 179. So let's do that between 175 and 185. And I'm make sure that I change the grid lines to 1. Yes, so this is 1, this is the x's and the y's are 1. Now when I graph that, I get a zoom in of that point. All right, and I can see that the closest would be 215, this point here, 215 and 179. Then I have 215 and 178 and 216 and 178. So these are the closest numbers, the closest points, or with whole numbers of bicycles inside the feasible region. All right, and now I go back to my document. I have taken a snip of that last diagram. Yes, and I state those points. The closest points where x and y are integers and they are inside the feasible region are 215, 179, 215, 178, 216, 178. And then I plug those values into the objective function for profit, yes, and I get the highest profit of 45,130 if I make 215 boys bicycles and 179 girls bicycles. And the last thing I need to do is make a statement about my Findings: for 215 boys bicycles and 179 girls bicycles, we get the maximum profit of 45,130, and we are still inside the feasible region. All constraints are met. And this is the example worked to excellence level. Thank you for watching.